Okay, you can mark your attendance. Google link has been provided in your class group. So I think you already have this material with you. Even I have uploaded in the classroom. So if required, I'll be uploading this today evening also. You can download and use it. Okay. So I think I will be having 5 more hours, including this hour. I'll be having 5 more hours by considering 4 hours next week. But in that 1 hour, I will be taking for quiz conduction. Okay. So Monday there will be quiz 2 for you. MEC quiz 2 Monday. So apart from that, I'll be getting 4 hours. So I think I will be finishing with 4 hours. Okay. It is quite simple only, but the thing is that you should understand some basics. So try to understand. If any queries, you can post in the Google Classroom. I'll be clearing your doubts, but no one is posting the doubts. That's the fact. So if you have any doubts, you can contact me through Google Classroom. I'll be clearing your doubts. Okay, so let me start the fourth module. So here, I think ma'am has already given this material, no? Even I can post today evening also, no problem. So just download and keep it in your personal PC. So this module can be divided again into two sections. So in the first section, we'll be discussing the cascode amplifier. Okay, that is normal amplifier will have its own drawbacks of gain, bandwidth, etc. But the cascode amplifier is trying to increase our gain. So this module will be dealing with the cascode amplifier, its working, its small signal analysis, that is the different parameters of cascode amplifier will be derived. Followed by that, the frequency response of the cascode amplifier will be analyzed, that is how does the amplifier will respond against different frequencies, or how you can find the cutoff frequency of a cascode amplifier, because after cutoff frequency you are expecting the gain to decrease, isn't it? The gain will decrease after a particular cutoff frequency. So you have to identify that particular cutoff frequency of a cascode amplifier by using frequency response analysis. That is the second part. Okay. I repeat, in the first part, we'll be dealing with the small signal analysis, where you will be deriving different parameters of an amplifier like gain, overall gain, uh, typical gain, input impedance, output impedance, everything we'll be discussing. Followed by that, we will be deriving the frequency response, where you will be calculate the expression for FH. What is FH? FH is the 3 dB cutoff frequency. And what is the speciality of 3 dB cutoff frequency? After that frequency, your gain will start decreasing. So you have to derive that value of FH. So followed by these two, next we will derive or deal with some configurations of cascode amplifiers and its applications. So the first application is cascode current source. That is, you can use this cascode version or cascode connection to design a current source. Current source is nothing but a discrete circuit which is used to produce a definite amount of current which is required for an IC to operate. You know that in an integrated circuit you will have different discrete components connected together. Each and every discrete components will have different currents. Not necessary that all will be working with the same current. You don't misunderstand that. Okay, so different part of the IC will have different current. Some require 5 milliamps current, some require 100 milliamps current. So it is entirely different. So you have to steer the current from one part of the location of the IC to another location. Okay, so you will be generating a current source at one location, and from that location you have to steer the current to other part of the ICs. So for that you require a current source as well as current mirror. So to build a current source, you can have a cascode configuration that we are discussing in the third part of this module, that is cascode current source. Okay, so cascode current source is nothing but a circuit which is used to build a, or the cascode configuration can be used to build a current source. Again, these are the three different versions of cascode current source. This is a basic fundamental concept of current source by using cascode configuration. The same thing, the circuit can be remodified into three different configurations. It has its own features and benefits. So that we are looking into double cascoding, folded cascoding, and bi-CMOS cascoding. You know what is bi-CMOS? It is combination of bipolar and CMOS. That is BJT and MOSFET. So this is what is the first part of this particular module is dealing with. Now in the second part, we'll be discussing about the mirror circuits. You know what is mirror actually, isn't it? The responsibility of a mirror circuit is to steer the current from one location to another location. Understood? That is, you might have generated a required current at one point of a circuit or one point of an IC. So maybe it's 100 milliamps. From this 100 milliamps, you have to generate 50 milliamps. Do you again design another current source of 50 milliamps for the second part of the IC? Not required, no, because the hardware will increase. Again, power consumption will increase. So what is our goal is to form a 50 milliampere current from 100 milliampere. Okay, that is nothing but your steering. So this steering can be done by using simple circuits like mirror circuits. So here we'll be defining different mirror circuits like first one cascode MOS mirror, that is using MOSFET and cascode configuration. Will be designing mirrors, followed by that bipolar mirror using BJTs. Then another scientist, that is a researcher, has designed another mirror which is known as Wilson mirror, which is named after his name, that is Wilson current mirror. Then Wilson MOS mirror, again the Wilson current mirror is BJT version, Wilson MOS mirror is MOSFET version. Same circuit, same configuration, but the BJT has been replaced by MOSFET. Again another researcher, Whittler, named a scientist, he has designed another current source, that is Whittler current source. So these are all current sources and current mirrors which you can use in different applications like what we have discussed in module 5. In module 5 we had discussed many transistor pairings, isn't it? And along with that we have derived the differential amplifier also. We have deal with the differential amplifier also. So in this differential amplifier and in this transistor pairing circuits, you require current source or current mirror circuits, isn't it? So these current source can be designed by using these particular mirror circuits like MOS mirrors, Cascode MOS mirrors, Whittler source or Wilson source, whatever it may be. Okay, so this is the second part of the module. Understood? So this module is again divided into the first part. You will be dealing with the cascode amplifier and different versions of cascode circuits, and in the second part we'll be dealing with the current mirror circuits like BiCMOS, then bipolar MOS, bipolar mirror, Wilson current mirror, Whittler current source, etc. Okay. So now going to the syllabus. So first is cascode amplifier. It is not cascade, it is cascode. There is a clear-cut difference between cascode and cascade. In cascade, obviously, we'll be dealing with similar stages. Okay, if you are using a multi-stage common emitter amplifier, in the first stage also you will be using common emitter, in the second stage also you will be using common emitter. So these are all cascade. Okay, but here we are not using cascade, but instead that we are using cascode. Okay, and what is the difference between cascade and cascode is that in Cascode, we'll be using two different configurations simultaneously, just that like what we have mentioned in the previous module. Okay, so here we are using two configurations. So one is common source and the other one is common gate. Okay, I repeat, here we are going to connect two different configurations simultaneously in one amplifier. That is what is known as cascode connection. That is, the two configurations are, one is common source and the other one is common gate. So we can exploit the benefits of these two configurations simultaneously in one circuit. Okay, so we'll be using common source, along with that you will be using common gate configuration also. Understood? And what is the advantage of this is that, see, the advantages being mentioned in the second point. The basic idea behind this cascode amplifier is to combine the high input resistance and large transconductance achieved in common source. So this is the benefit of common source. Okay, I repeat, what is the benefit of the common source? Common source will be providing high input impedance and large transconductance. Okay, so this is a benefit offered by common source. At the same time, common gate is offering high frequency response. What do you mean by high frequency response? Better performance of the amplifier in high frequency. Normally, every amplifier, when we go for the high frequency, your gain will decrease, isn't it? Your output will decrease. So that is affecting the performance of the amplifier. So when you have a high frequency response, means that is beneficial to the users and the designers. Okay, so this you can get in an amplifier if you use a common gate configuration. Understood? And also, other than this particular property, this common gate is also used for as buffering property. It also provides a buffering property also. So these two benefits are simultaneously exploited in one circuit. That is what is known as cascode. Okay, I repeat, in a cascode amplifier you are using two configurations. One is common source and the other one is common gate. Common source benefit is, what is a common source benefit? It is providing high input resistance and large transconductance. And at the same time, common gate is offering better high frequency response and buffering properties. So all these four properties you are integrating together in one amplifier. That is what is known as Cascode. Understood? But the problem here is that generally this is used to increase the gain. Okay, generally it is used to increase the gain, but what happens is that if you are increasing the gain, your bandwidth will decrease. See, you have to read this particular point. Read this point. It can be designed to increase the gain. For example, if I have an amplifier of gain 10, okay, normal amplifier, but what my intention is to, I have to increase my gain. So what I'll do is I'll be cascoding this common source with common gate, so that my amplifier gain I try to make it as 20. But unfortunately what will happen is your bandwidth will decrease. Okay, so if you are trying to increase the gain, means your bandwidth decrease. How much times your bandwidth is going to decrease is same as that of the increment that you felt in your gain. Okay, increment that you have achieved in the gain. For example, you are able to double your gain, means you are making your bandwidth half. Okay, if you are tripling the gain, means you will achieve 1 by third of your bandwidth. So that is the effect of cascoding, not cascading. Cascading is different. You are achieving here you are doing cascoding here. Cascoding means connecting different configurations. One is common source, the other one is common gate. First stage will be common source, the second stage will be common gate. Understood? Because of exploiting, using all the four benefits together. Okay, common source has two benefits, common gate has two benefits, so all these four benefits can be combined in one particular circuit, and the effect is increase in gain and decrease in bandwidth. Understood? But it also considered as a single amplifier stage, though it is having two different stages, but we will not call it as a multiple stages, because multi stages means you should require two different configurations, then only you will say that it is a multi-stage amplifier. Okay, two same configuration, sorry. For example, if you're connecting CE means definitely it will called as a double stage amplifier. But unfortunately here we are using one CG and the other one is CS, isn't it? So this is having two transistor configurations simultaneously using in one amplifier. But still we are not calling it as a double stage or multi-stage, but it is acting as a single stage amplifier. Any doubts with this introduction part clear now? Any doubts with the introduction part clear? See, only if you know the fundamentals, it will be very easy for that analysis part will be very easy. Okay. Second part is quite easy. This current mirror part is quite easy. Only some analysis is required in this part, small signal analysis. But these points are very much easy only. This part. Okay, that you can score very good marks in this portion. So try to understand the concept and then write and practice the derivations. Otherwise, you will feel that it is very difficult. So don't think that MEC is a very tough subject to pass or to score high marks and all. So you should prepare your own notes. Okay, don't read my notes as such and go and write the exam. You will not be able to reproduce in your paper. Okay, to produce in your paper properly, you will have to practice by yourself. Okay, all the derivations you have to practice and get into the results. Fine. Now, first part, MOS cascode. So this is a basic arrangement of a cascode configuration. I told you this is common source part and this is common gate part. Understood? So why it is common source? Why it is common source? Because I'm taking input to the gate and output is from drain. Okay, I'm taking the output from which terminal? I'm taking the output from drain terminal, because this drain is given to second stage. The drain output is given to the second stage. So obviously the drain is your output of first stage and source is common to both gate and drain. Okay, source is common to both gate and drain. So this is known as common source configuration. At the same time, when you come to the second stage, you are giving input to source. You are giving input to source from the previous stage. Okay, and you're taking output from drain. So which is your terminal that is common? Gate is the terminal which is common to both the transistor or both the inputs and outputs. So this is known as common gate configuration. Understood? So this is common source and this one is common gate. So now you have cascoded your common gate and common source together. Okay, common gate and common source together to form a cascode amplifier. Okay, and the peculiarity of this cascode amplifier is that you are going to achieve the benefits of two configurations simultaneously. Okay, now going to the analysis, small signal analysis. You know what is small signal analysis, isn't it? You know what is small signal analysis? Small signal analysis is a method to find the parameters of an amplifier. Okay, while doing small signal analysis, what you have to do, you are not going to take any of the constant power sources or current sources into consideration. Okay, you will not take care, or you will not take any of the constant power sources or constant current sources into consideration while performing the small signal analysis. All the DC voltages, all the DC currents will be deactivated. Okay, so the same circuit, this is a basic circuit, and you will be converting this basic circuit into a small signal equivalent circuit from which you will be performing the analysis to derive the parameters. Understood? Okay, so this is your transistor Q1, this is your input Vi, and this is R01. What is R01? R01 is the output resistance of Q1. Okay, R01 is the output resistance of Q1, which is something internal to the transistor. That is why I have not shown in the previous diagram. Okay, the main diagram I have not shown R01. R01 is the output voltage, or V early voltage divided by drain current. You know the expression for R0, isn't it? From the first module we have been studying the same thing. Okay, small letter R0 is the internal output resistance, which you can define simply by the equation early voltage divided by drain current. So to perform the small signal analysis, you have to take this particular resistance into consideration, even though it is not mentioned in the main circuit diagram. Now you know that once you draw the CS configuration, next thing is you will be drawing the common gate configuration. But in the gate voltage, the gate terminal, you have a voltage here which is nothing but a bias voltage in the proper diagram, the main diagram. But as of now you will be deactivating that V bias and you will be putting a ground over there, because we are performing the small signal analysis. Okay, and similarly you will be using R02 across Q2, and from the drain only we are taking output. You know that, isn't it? From the drain of Q2 only we are taking the output, so we will be connecting a load resistance across which we will be taking the output. So RL is connected at the drain terminal. And did you note that VDD has been deactivated? Similarly, you have deactivated this current source capital I. Okay, VSS, everything have been deactivated. See, V bias have been deactivated, VDD and current source, all the three constant voltage and current sources have been deactivated, and you have only shown the input voltage Vi and the two transistors along with two output resistance and load resistance. So understood how we are going to draw the small signal analysis, I mean equivalent circuit. Any doubts with this respect to this particular circuit? Okay, any doubts? Now what we will do is we will be writing the equations for R in, R out, and here there is one more R in. Okay, so first these two input and output resistance will be writing. This you have to study from common gate derivation, which you have derived in third module. Okay, so you should by heart these results. Already we have derived that result, so you can, after this class you may check going back to the third module and take the analysis of common gate. So in the small signal analysis of common gate amplifier with the active load, you have derived the equation for input resistance and output resistance. So this is R into means input resistance of Q2, which is nothing but common gate. This is common gate. So it is given by 1 by GM2 plus 1 by GM2 plus RL divided by AB02. So this you have already derived. So I don't want to derive this again. So directly you can take this result and mark in the circuit diagram. You know what is GM2? GM2 is the transconductance of Q2. GMB2 is the transconductance due to the body effect of Q2. AV02 is the gain of transistor Q2. Okay, open circuit voltage gain of transistor Q2. RL is the load resistance. Similarly, here you have mentioned R out. Again, this thing, same thing we have derived for the common gate, that is output resistance, which is equal to R02 plus AV02 into R01. R02 is this resistance, that is output resistance, which is internal to the transistor. AV02 is the gain of the second transistor, second stage, and R01 is the output resistance of the first transistor. Okay, so that, and again one more thing, AV02 you have to write. What is AV02 also? AV02 is nothing but the open circuit out voltage gain of second transistor. Open circuit voltage gain means if you are not considering the load resistance into account, you know what is open circuit. Okay, while writing the open circuit voltage gain, what you have to do, you will not take RL into account, you have to remove RL and then find the gain. Okay, so that equation is already we have derived from the common gate configuration. So these three equations, one is equation for R into, other one is equation for AV02, and third one is R out one. Okay, so R out. So R out, R into and AV not to, these three equations you have to by heart. Okay, that is you have to get in from the common gate derivation part. So next thing what you will do is you will be writing the equations for total output resistance at the drain. So at the drain you are having R02 as well as RL, isn't it? So the total output resistance will be equal to R01 parallel R into at the drain. So we are not considering RL. So at the drain you are having R02 as well as this R into is applicable to this also, isn't it? R into is nothing but the input resistance of Q2. Okay, R into is the input resistance of Q2. At the same terminal only you are having R0 1 as well. Okay, R0 1 as well. So RD1 is nothing but RD1 is a drain resistance of Q1. Okay, so while writing the drain resistance of Q1 at the drain you are having R01 and at the same time this R into is the input resistance of common gate, but even though that act as output resistance of Q1, isn't it? Because output of Q1 is nothing but the input of Q2. So while calculating the input resistance of Q2, you must be aware of the fact that it is considered as the output resistance of Q1. Understood? If Rn2 is the input resistance of Q2, at the same time it is equivalent to the output resistance of Q1. So while writing RD1, what you have to do at the drain terminal, you are having R01 along with R01, you are having this also Rn2, which will be parallel to each other. That is represented in equation number 3. Okay, now already we have written this R into, you know that R into is this equation, so you can substitute over there and write. So this is the first derivation of input resistance. Okay, so just all the resistances we have mentioned. Okay, so one resistance is R into, second resistance is RD1. RD1 is nothing but the output of Q1. R into is the input of Q2. Okay, now going to the second subheading, R out, that is total resistance. See, R out, while writing R out, we have written this thing. R out is equal to R02 plus AV02 into R1. Actually, what is this? This is the output resistance of a common gate transistor. Okay. There also you can substitute the equation for AV02 because AV02 is the open circuit voltage gain of common gate configuration, which we have already derived from the previous analysis of common gate amplifier. So write those equation as such. AV02 is 1 plus GM2 plus GMB2 into R02 multiplied by R01. So next thing what you will do is you will be taking this R01 inside, open the brackets and simplify this. Okay. So when you observe this particular equation, what you feel is here, see, you know the value of GM. GM is quite big. GM is a transconductance. Okay. But R0 it is quite less. The value of R0 is very less when compared to GM. So whenever you have a factor multiplied by GM, it will be large when compared to R0 alone. Okay. So all these two terms, it is having only small R0. Okay. It is R0, which is a distinct term. Okay, which is a distinct term and it is alone. Okay, along with that there is no amplification factor over here, or there is no conductance factor here. But when you take this third term here, you are having a factor which is called GM2, that is a transconductance of second transistor, which is quite high. So this can also be neglected. Why? Because GM2 is nothing but a conductance due to body effect. Okay, that is very much small when compared to GM. So this is also neglected. So approximately the output resistance can now be called as GM2 into R02 into R01. And what is this GM2 into R02? It is A0. Okay, that is a gain, intrinsic gain of second transistor. Understood? So a GM2 into R02 is a gain offered by Q2 actually. So whatever the gain that is offering by Q2, that is multiplied by the output resistance of Q1, then you will get the total R out. So with this, what is our conclusion is you are able to get a large output resistance which is equal to A0 multiplied by R01. See, if you have not used this common gate, means what will happen? See, forget about this common gate in the upper part. Then what is the output resistance? Okay, if you're not considering this common gate part, means your output resistance will be normally it is equal to R01. It will be equal to R01, isn't it? You know that R01 is very small. So if your output resistance is very small, means you will have excessive current flow through the load that will dissipate a very large current or very large power also, because power is equal to V into I. Okay, so excessive current flow through the load will take more power consumption. Okay, will lead to more consumption. So we have to increase the output resistance. So to increase the output resistance, what we are using? We are using this particular configuration. Which configuration? Common gate. So due to effect of this common gate only, I was able to get the output resistance which was equal to A naught times of R naught 1. Okay, so in place of R naught 1, now I am getting A naught times of R naught 1, where A naught is a gain offered by second transistor. Okay, whose expression is given by gm2 into r02. So this a naught is nothing but gm2 into r02. You know, we have already derived the equation for open circuit voltage gain in previous modules. Okay, so you have to link that third module and fourth module. Okay, so in the third module we have already derived the equation for gain of a common gate transistor. It is given by a naught gm into rd is nothing but a. Okay, here instead of rd you are having r01. So gm into r01 is your total gain A0 of a second transistor. So whatever the gain offered by the second transistor, that gain multiplied by the output resistance of the first transistor, that will get you the overall output resistance of the entire amplifier. Understood? So the conclusion is, with this cascode amplifier, I am able to get a large output resistance which is equal to A0 multiplied by R01, where R01 is the output resistance of first stage. Which is the first stage here? Which is the first stage here? It is common source stage. Okay, so in the common source you are having r01. So that r01 multiplied by the gain of q2, that is the overall output resistance r out. I hope you understood. Hmm? So till now we have derived the equation for output resistance as well as the input resistance. Now going to the open circuit voltage gain. Okay, it is quite simple only. So you know that here you are having two stages. Okay, first stage it is common source, second stage is common gate. So as far as the first stage is considered, that is Q1, your output is marked as V01. Okay, so consider that in the first stage your output is V01. This is your output. See, this is the output of the first stage. This is your input of the first stage. So by dividing these two, you will get the gain of first stage, isn't it? So V01 divided by Vi will get you the gain of the first stage. You know the gain is nothing but Gm into Rd. Here at the drain you are having R01, isn't it? So the gain of first stage is Gm1 into R01, because I have to put 1 in the subscript because it should be specified that this gain is applicable only for first transistor, that is common source transistor. Understood? So this can be called as minus A01. Why I am putting minus? Because this is inverting amplifier. You know that common source is an inverting amplifier, so you should be able to put a negative sign over there. So it is offering a negative gain which can be represented as minus gm1. What is gm1? Transconductance of that transistor into its output resistance. Okay, now coming to the second stage. In the second stage your output is V0. In the second stage your output is V0. Again V0 is nothing but gain into input, isn't it? V0 is nothing but it is gain into input. What is the input to this particular stage? What is the input to this particular stage? It is nothing but V01. This V01 is cascoded with common gate, isn't it? So V01 is acting as the input to the second stage. Okay, so output is equal to gain multiplied by input. Output is equal to gain. Which gain? Second stage gain. Second stage gain is AV02 multiplied by input. What is the input actually? What is the input? It was nothing but minus A01 into VI, isn't it? That is the gain of first stage into VI. Okay, so whatever be the input voltage Vi, that input is getting amplified by A01 times by this particular transistor. So this amplified output is given to the second stage as input. Again the second stage will amplify and provide a new output V0, which is nothing but the gain of the second transistor multiplied by the output of first. Output of first is minus A01 into Vi. But here you won't put minus here because this is not an inverting amplifier. Okay, as far as the second stage is concerned, common gate, it is not an inverting amplifier, so you won't put minus over there. Okay, so the overall voltage, the overall gain. Okay, so this is the, as of now, this is the equation what I have got. V naught is equal to minus AV naught 2 minus AV naught 2. What is AV naught 2? It is a gain of the second transistor into the input to the second transistor is A naught 1 into Vi. Now I take Vi to the out, left side. I'll take Vi to the left side, so that V naught by Vi is the overall gain AV naught. Okay, you know that when you consider this total amplifier as such as whole, V naught is the final output and Vi is the initial input. So when you take this ratio V naught by Vi, what is the answer? Answer is minus A naught into A naught. Okay, consider that the two gains are same. Consider that the intrinsic gain of these two transistors are same. So we don't mention like AV naught 2 or A naught 1 like that. You don't need to mention. Put it as A naught and A naught. So Vi you can take here. Okay, Vi you can take left side. So in the right side you are having only minus A naught 1 into AV naught 2. Those two gains are similar. Can assume that the two magnitudes of the both the gains are same. So the answer will be minus A naught square. Okay, and Vi is taken left side. What is V naught by Vi? V naught by Vi is the overall gain AV0. Okay, it is AV0. Why AV0? Because we are doing we are doing not voltage gain, we are doing open circuit voltage gain. What is the property of open circuit voltage gain? When we are calculating open circuit voltage gain, we will not consider the load resistance into account. Okay, so in the normal circuit diagram we had a load resistance, isn't it? We had a load resistance, but while calculating the open circuit voltage gain, we will not use any load resistance. Did you observe any load resistance here? No, because I have opened it. So since the circuit is being opened, load is opened, there is no current here. Understood? There is no current. That is why I have shown it as 0. Okay. Why I have shown 0 current? Because I have open circuit. Across an open circuit, can you expect any current flow? It is having infinite resistance, isn't it? So 0 is the current. So whatever be the current, output current, it is equal to input current because it is buffer only, isn't it? This is common gate. A common gate's property, you know that common gate property, it is buffer. It acts as a buffering device. Buffering device means input current is equal to output current. Since I'm expecting 0 output current here, what is the input current? Input current is 0. Okay, current 0 means what is resistance value? Current 0 means what is the resistance value? Resistance value is infinity. So R into is equal to infinity. I hope you understood. Okay, I'll repeat again. This is the open circuit voltage gain. So I have not considered RL at the output stage. So because of this open circuit, the output current will be 0 because across an open circuit, the current will be always 0. So this will be your current. Okay, so when this output current is 0, input current is also 0 because this is a buffer. What you know, what is the property of a buffer? Buffering property means there is no change in current. Whatever be the input current, that will be passed to output current, output terminal. So since output terminal is equal to 0 current, input terminal is also having 0 current. 0 current means resistance is maximum. So I have mentioned R into is equal to infinity over here. Clear now? And this is the equation for overall gain, which is equal to minus A naught square. And you know what is A naught? A naught is GM into R0. As of now, don't mention R01 or R02 because I have assumed that both the resistance are same. Okay, since both the resistance are same, then only you can write AV02 is equal to A01. Okay, so since the both the gains are same, I can write that GM1 into R01 is equal to GM2 into R02. That is same. So just I put GM into R0 the whole square. So this is the overall gain. This is the overall gain of the cascode. So how much gain you are expecting actually? You are expecting only A. With a common source amplifier, you are expecting the gain A0. But when you cascode, your gain has squared. Understood? So that is the speciality of a common, cascode amplifier. Which gain is this? Is this is an overall gain? No, this is open circuit voltage gain. So the speciality of open circuit voltage gain is that it is able to, we are getting a gain which is nothing but squared gain of a normal amplifier. Normal amplifier means CS. CS is having gain A0. But when you are cascading the CS with the CG, again CG is offering some gain which is equal to A0. That A0 multiplied by A0 which is equal to A0 into A0, that is A0 square. This is the overall voltage gain of a cascode amplifier in open circuit case. That is why it is called as AV0. Okay. Any doubts with this part? Clear? Now we'll be dealing with AV. Okay. So till now we have derived AV0. AV0 means it is AV0 means it is the open circuit voltage gain. Now this is the typical voltage gain or the overall voltage gain. Okay. Earlier we have done AV0. AV0 is the open circuit voltage gain, and this is voltage gain. Hmm. Now to calculate the voltage gain, what you have to do is you have to draw this particular circuit diagram. Okay. So where did you obtain this particular circuit diagram from is from this portion. Okay. So here I am incorporating the load resistance. Here I'll be adding. See, please don't disturb. You can mute yourself. You can just mute yourself. So here to calculate the voltage gain, the difference between the open circuit voltage gain and the typical voltage gain is that while calculating the normal voltage gain, you have to consider the load resistance into account. Okay, so here you will be putting the load resistance RL. In the earlier diagram, I have not taken any load resistance at the output. Understood? Got the difference? While calculating the open circuit voltage gain, you will not consider the load resistance. But if you are calculating the normal voltage gain, you will be connecting a load resistance at the drain terminal. And apart from that, there is R out. You know what is R out? R out is the total output resistance, and you have achieved the equation for R out also earlier. The previous analysis, you have derived the equation for R out. You know what is R out? R out is nothing but A naught times R0. Okay. Actually, R0 is the resistance of one amplifier, but that particular resistance will be multiplied by capital A0 to produce the overall output resistance. Okay. Small letter R0 is the output resistance of the stage. Which stage? Common gate. Sorry, common source. Okay. But when you are cascoding common gate along with the common source, you are obtaining a very large output resistance which is equal to A0 into R0. That is what is mentioned here. Okay. So this is your R out. This is your load resistance RL. And this one is your input to the second stage. Okay, input to the second stage means it is nothing but A naught into Vi. And what is the overall output? Overall output is Vi into A naught into A naught, because there are two amplification, isn't it? Common source is amplifying, again that output is again amplified by common gate, so the overall output is A naught square into Vi. Okay, or minus A naught square into Vi. Why we are putting minus? Because I have to consider the polarity of common source, because common source is an inverting amplifier. So for that you will be putting a minus here. So this is the overall output without load. Okay, I repeat, this is the output of the cascode amplifier without any input. Without any input means without load actually. Without input, sorry, without load actually. Not without input, without load. Okay, so without load you are getting the output which is equal to A naught square into Vi. Eh? And what about this? This is your output resistance and this is your load resistance. Now you have to calculate V naught. V naught is the actual output with the load, across the load. So we will be applying voltage divider rule. See, you don't require this particular circuit. Okay, don't be confused. You don't require this particular circuit diagram. You can proceed with this itself. That is quite simple. Understand? Okay. So by just applying a voltage divider rule, you will be able to get the value of V0. By simply applying a voltage divider rule, you can get the value of V0. So how will you find V0? V0 is the voltage across RL, isn't it? So Vi into, that is overall input, into input is minus A0 into A0 square into Vi into the voltage, the resistance across which you are getting the output, that is RL, divided by total resistance. I hope you know how to apply the voltage divider rule. Being a 6th semester students, I don't want to explain all those. Okay. V naught is equal to the overall input into the resistance across which you are taking the output, that is RL, divided by the combination of the two resistance, that is RL plus R out. What is R out? A0 into R0. Now what you will do is take Vi to the left side. So this will be the ratio. And you know what is ratio V naught by Vi is AV. Now you will not put AV0, you will put only AV. Okay. So this is the equation for AV. Okay. And this AV is equal to GB. GB is nothing but overall voltage gain. This is the typical voltage gain. The earlier one, it was AV0, that is open circuit voltage gain, and this one is GB. GB is the overall voltage gain. Overall voltage gain is nothing but the ratio of Vi by V sig. It is not V naught by Vi, it is V naught by V sig actually. I think you know the difference between V naught by Vi and V naught by V sig. Ma'am has told earlier module and all, she might have been discussed. V naught by Vi is the conventional gain. Okay. But in certain cases, this input to the transistor may not be equal to the original signal which you have given for amplification, because the drops you have to consider across the signal resistance are sick. I repeat, whatever you have given, that is the input signal. Input signal is Vsig, and don't think that this entire Vsig will appear across the input terminals of the transistor, because some sort of signals they might be dropping across your resistance which you have physically connected at the input terminal. Okay, so Vsig will not be equal to Vi in certain aspects if Rsig is not Rsig is there. Okay, if you have a precise value of Rsig, across Rsig you will experience some voltage drop. Remaining voltage will be coming across the input terminals. Thereby you can say that Vi will not be equal to Vsig. But as far as this particular circuit of cascode amplifier is concerned, see, take that circuit diagram. Did you connected any signal resistance there? You don't have any input signal resistance because Vi is as such it is coming to the input. So the speciality of cascode amplifier is you will not connect RSig, because when you connect RSig, what will happen is there will be some drop. So Vi will not be equal to Vsig. But in certain cases you have to connect Vsig. That later I will be telling. Okay. So with RC case is entirely different, and without RC case is entirely different. Don't confuse. Okay. So as of now, what our intention is in the small signal analysis, our requirement is to find the equation for overall voltage gain. Okay. So to find this overall voltage gain, you have to find the ratio of V naught by V sig, not V naught by Vi. V naught by Vi is AV. This is V naught by Vi. And V naught by V sig is called as GV. GV is the overall voltage gain. But when you are not connecting RSig, when you have not done any RSig, means there is no drop across RSig. If you have not connected any resistance at the source terminal, means there is no drop across RSig. If there is no drop across RSig, means what will happen? Vi will be equal to Vsig. So whatever the input you have provided to the amplifier terminals, they will be provided, they will be getting directly into the MOSFET's terminal. So Vi can be equal to Vsig. So obviously this ratio V naught by Vi will be equal to V naught by Vsig, and now it can be called as GV instead of AV. So previously I have called it as AV, now I am calling it as GV because AV is equal to GV as far as this particular relation is concerned. So there is no difference between AV and GV, it is same only. Understood? Now next thing is, what is the effect of this cascoding actually that we are trying to find out. So till now we have derived three quantities in the small signal analysis. The first case is the input resistance, then we derived the equation for the output resistance, then the open circuit voltage gain AV0, then voltage gain AV, and lastly the overall voltage gain. So five parameters we have derived for the cascode amplifier. Okay, now what we'll be doing is I'll be drawing this particular diagram. Based upon this, I'll be deriving some conclusions. That will be the important features of these two amplifiers, these two stages. Okay, what is this actually? This is your GM into VI. GM into VI, as you know that it is drain current. This is the equation for drain current, and this particular equivalent circuit is only applicable to the common source stage. Okay, please keep it in mind. Common source is a first stage, and we are drawing some equivalent circuit of this stage in order to derive the equation for the gain of that particular stage alone. Okay. So for that, I'll be drawing a small signal equivalent circuit. So in that small signal equivalent circuit, you will be representing a current. That current is nothing but GM into VA. Drain current is GM into VA. VGS actually. VGS is VA. You know that ID is equal to GM VGS. You have learned in first module. Drain current equal to GM into VGS. But this VGS is equal to VA, isn't it? The entire input VA, take that circuit diagram and see the entire input Vi, it will be coming across the gate source terminal because there is no intermediate resistances over there. So ID can be called as GM into Vi. This ID will be splitting into two values, one across R0 and the other one across this. And what is these two actually? This is R into, isn't it? R into means it is the input resistances of second stage. The second stage is appearing at the output of the first stage. So along with R0, there is an effect of another resistance, which is nothing but the input of the second stage, input resistance of the second stage, which can be denoted by this particular equation. So the overall resistance is R0 parallel this particular 1 by Gm plus RL divided by A0. Okay. Now we are trying to find out V01. V01 is the output of the first stage. That is common source stage. Output is equal to current into resistance. You know that voltage is equal to current into resistance. What is the current here? Current is GMVI. What is the resistance here? Do you have only R0? No. You are having a resistance which is equal to the input resistance of the second stage. So you have to consider these two resistances together in parallel effect and put a minus sign also along with. Why you are putting minus sign? Because you know that CS is a common source is an inverting amplifier, so you put a minus sign and take Vi to the left side. So this is the actual gain of CS stage. Earlier we just denoted that the first stage is having gain A01, that only we told. But actually what is this A01? It is given by equation number 12. And A02 is the gain of second stage. Like that we told, no? And the overall gain is nothing but A0 the whole square, A0 the whole square, where A01 into A02 is the overall gain. So there A01 is a gain which is relevant to the first stage alone. That is what we have derived from equation number 12. Now, this gain will change according to load. You know that always the gain of any amplifier will be changing with respect to load because the value of the load is going to affect our gain. You know that when you are operating fan, you will have another power. When you are operating TV, you are having another power consumption. At the same time, when you are using iron box, you will be having different power consumption. So the entire power consumption is based upon the load that you are connecting. Okay, in your household equipments case. Similarly, in the amplifier also the gain will be determined by the load resistance. So the load resistance is going to determine the actual value of the gain that is given in equation number 12. Okay. So how this load varies and how the variation of the load is affecting our gain. That is what we are trying to learn. So case 1, when load is A0 into R0. So this is one load. This is one case of load. That is we are trying to make this load resistance equal to A0 into R0. You know what is load? We have connected a resistance to the drain terminal across which you are taking the actual output. Okay, so that load resistance should have an apt value, a desirable value we have to take. That desirable value of load resistance is setting your gain actually. Okay, that we are trying to find out. So suppose that you set your RL equal to A0 into R0 and what happens we are checking. Okay, so in this RL you are putting this value. So what happens? A0 into R0 by A0, this A0 will get cancelled, isn't it? I repeat, this case you are substituting here. Understood? So when you substitute RL with A0 into R0, this A0 and this A0 will get cancelled. So the remaining term is only R0. Okay. And here R0 parallel, GM is very large. You know that GM is very large. So 1 by GM will be neglected. 1 by very large value can be neglected, isn't it? So 1 by GM can be neglected. So the only left term is R0 here. So that R0 parallel R0 will become R0 by 2. And GM into R0 is A0. So A0 by 2. Okay, so the first stage is offering a gain of A0 by 2. Understood? V0 1 by Vi is nothing but the gain of first stage. So the first stage is offering a gain of A0 by 2. Now, same condition we will be setting for the overall gain also. We have already derived the overall equation gain AV with the load, isn't it? What is AV? This is the equation A0 square RL divided by RL plus A0 into R0. In that also we will be setting the same condition RL equal to A0 into R0 and check whether what we are getting. See, when you put RL like A0 into R0, it will go like this. In the denominator part, you will have 2 into A0 R0, which will be cancelled. So in the denominator, the only term left out with is R2. Okay, so the gain becomes the overall gain AV. AV is equal to GV in this case. So we can call it as GV also. Okay, so AV is equal to minus A naught square by 2. See, this is a gain. This is the total gain with the load. When that load value is equal to A0 into R0, be careful. The condition you have to be very careful. Okay, you will not get this gain in all cases, only for this case. Okay, only if you are setting RL as A0 into R0, then you will get this gain. This is fairly good, no? This gain is fairly very much high. A0 square by 2 is very good. So this particular value of load resistance is appreciable. It is desirable for us. So when you are putting a gain, a resistance across a cascode amplifier, you should be able to put this value. Load resistance value should be equal to A0 into R0. Then only you will get this particular gain AV, which is equal to minus A naught square by 2, because it is very much high only. At the same time, when you are putting R0, what will happen? Try with the other extreme. Okay. As of now, I have put RL equal to A0 into R0. Now I am trying to put RL equal to R0. Then what will happen? Same procedure. Initially, I'll be calculating V01 by VI. This was the expression for that. There I am putting A0 as GM into R0. Okay. See, simplify these two. Simple max it is. Okay, you can simplify. And the final thing that you will get is 2. Answer is 2. So this is again which is providing by the first stage. Again, you will be putting in the overall voltage gain equation. You know that the overall voltage gain equation you have already derived in equation number 11. There I will be putting RL as R0 and take R0 common, it will get cancelled. So the equation will be like this. 1 plus A0, 1 I neglected, so answer is minus A0. So which one is better? Here I got AV as minus A0. Here I am getting gain as minus A naught square by 2, which is good. Minus A naught square by 2 is very high than A naught. Okay. So the conclusion is you should be able to set a load resistance RL whose value should be equal to A0 into R0. So this is the very much desirable condition for the load resistance, so that you can achieve a gain of minus A square by 2 for a cascode amplifier. Okay. Otherwise, what happens is if you are connecting a load of R0 or very small load, your output gain will be only A0, which you can achieve by a common source. No need to connect then common gate. A0 can be achieved by common source also. You don't require common gate then. Okay. So the thing you have to notice that you have to connect common gate along with the common source to get a cascode. Also, you have to connect a load. That load should be equal to A0 into R0, so that you will get a overall gain of minus A naught square by 2. Okay. So out of this minus A naught square by 2, I will be coming to the previous case. See, out of this total gain A naught square by 2, one gain is minus A naught by 2. The first gain is A naught by 2. Okay. So minus A naught by 2 is contributed by the first stage, and the remaining gain is A naught, which is offered by the second stage actually. So that the overall gain becomes minus A naught square by 2. Understood? I repeat, that is if you are using this particular value of load resistance, you can get a total gain of A minus A naught square by 2, out of which A naught by 2 is the gain produced by the first stage, and the remaining stage is offering A naught, so that minus A naught by 2 into A naught will become minus A naught square by 2. This is the overall gain. But contrary, if you are using only R0 as the output resistance, then the first stage is offering how much gain? Only 2. First stage is offering only gain 2. You are getting only gain 2, and the overall gain is minus A naught square, which is very small, and that can be achieved by a common source itself. Then you don't require common gate. Okay. So in order to exploit the benefit of common gate, you have to set a load resistance which is equal to A0 into R0, so that you will be getting a total gain of minus A0 square by 2, just as I have shown in the previous case. Now I'll be concluding today's class. You just read these two cases. What is note 1? Gain of the cascode is same as that of the gain of the single common source stage when R equal to R0. So whenever I am setting the load resistance equal to R0, the gain of the cascode amplifier and the gain of the common source stage, both they are same. So it is not showing any difference. But at the same time, at least when you are setting RL value equal to A0 into R0, you are getting a very significant gain. High voltage gain can be realized. That is the point. Okay. Understood now? The concept of cascode amplifier, hope you have understood. So in the next class, we'll be deriving the frequency response. Okay. Thank you all. Any doubts you can ask. Any doubts? Okay then, thank you.
మామూలు ల్యాప్టాప్ మోడల్ ఉంది కానీ ప్రాసెసర్ మోడల్ లేదు.